So far, with regards to the principles of hydrostatics, we've only focused on situations where the fluid was completely at rest. Now we're going to look in situations where the fluid may actually be in motion, but the motion is kind of restricted. It's going to be rigid body motion, right? And let's think of an example. So we look at a fish tank and a pickup truck problem. So you got a fish tank with water situated in it, and then it's sitting at the back of a pickup truck, and then the truck is accelerating. Maybe it's on a ramp entering a freeway. And so what's going on now is the fluid sitting inside the tank is now subject to a rectilinear acceleration. Okay, let's look at this problem. So if the fluid mass accelerates in the vertical direction, the basic hydrostatic equations become the following. All right, so partial p with respect to x equals 0. Let's put in our coordinate system here. Partial p with respect to y is 0. And then partial p with respect to z, the equation in the z direction is this expression over here. The right-hand side is not quite 0, right? Is equal to rho times any acceleration that the fluid might experience in the z direction. So this could be a situation, for instance, a fuel tank and a rocket that might be moving vertically upwards, right? So the rocket has an acceleration a sub z in the vertical direction. And so if I combine, if I take this equation, and now I can write this as an ordinary differential equation, dp dz, simply because p is neither a function of x nor a function of y, it's strictly only a function of z, right? So dp dz can be written as the ordinary derivative is negative rho g, which is what we've been doing in hydrostatics problems. But now if I allow for acceleration of the fluid just in the vertical direction, I'm taking the example of a rocket, not the case of a fish tank in a pickup truck problem, then this is the equation. So it looks very similar and should be fairly easy to analyze problems of that type. If in general the fluid accelerates both in the z direction as well as in the y direction, in the case of a fish tank and a pickup truck problem, perhaps the fluid may only accelerate in the y direction, right? So if it did that, then the difference is the equation in the x direction, dp dx is 0. There's no variation of pressure with respect to x. Equation in the y direction, dp dy is not 0 anymore. And the right-hand side has a sub y. And then the equation in the z direction is the equation that I had previously, right? So in this situation, p is not a function of x through this expression, but p is clearly a function of both y and z, because partial p with respect to y and partial p with respect to z are non-zero. So if I think of p as a function of y and z, remember the y and z plane is this plane, right? That's the horizontal direction y, and then the vertical direction z. And p can change due to changes in y and changes in z. That's what these two expressions are telling us, right? And I can express this notion mathematically by looking at the change in pressure, dp, and pressure can change because y can change and z can change. And this is what you get for change in pressure or the differential of pressure using calculus. So it's a partial of p with respect to y times dy, and then the partial of p with respect to z times dz. So this tells me the change in pressure just due to changes in y coordinate, right? So if I'm moving parallel to this direction, what is the change in pressure? That's what this expression is going to tell me. Whereas if I move in the z direction, this expression tells me what are going to be the changes in pressure, right? So each of these terms on the right-hand side have an interpretation. The first term is a change in pressure due to changes in y. The second term is a change in pressure due to a change in z. All right. So I plug in the expression for dp dy and I plug in the expression for dp dz from the equations above, from hydrostatic equations, and I get this result. Now, why is this result useful? If I go to the next slide, along a line of constant pressure, we know that pressure does not vary along that surface or along that line. In other words, dp has to equal 0. So if I restrict myself, for instance, in the case of a swimming pool, it will be a horizontal plane. There's no change in pressure in that circumstance. So in general, for a problem where the fluid might be accelerating as a rigid body in both the y direction as well as the z direction in the yz plane in the previous picture, then dp is equal to this expression. If I set this equal to 0, what this allows me to do is I can solve for the ratio dz dy and get that result to be negative ay over az plus g, right? Why is this significant? This is significant. It tells me if I have a fluid in a fish tank here, And if this fish tank were accelerating in the positive y direction only, not in the z direction, just in the positive y direction only, so this a sub y over here is non-zero. It could accelerate in the z direction. That doesn't really impact what the shape is going to look like, and so let's not worry about acceleration in the z direction. So dz dy in this case would be negative a sub y over g. So what that implies is the lines of constant pressure are going to be tilted this way, and such that the slope of this line dz dy is simply, the slope of this line is negative a sub y over g, and it's clearly negative quantity, and that's why the slope is decreasing, right? If you look at the red line over here, and if this is the y direction and this is the z direction, it clearly has a negative slope, right? So the fluid surface is going to be tilted, and instead of having the blue line, when the fluid is being accelerated in the y direction, the fluid surface is going to be tilted and it's going to appear as the red line. And the lines of constant pressure, so this is the line of constant pressure, so all along this, because it's exposed to the atmosphere, is going to be atmospheric pressure, and then the lines of constant pressure are going to look like this in this problem. All right. Previously, the lines of constant pressure look like this in the swimming pool problem, right? So in this case, the lines of constant pressure are tilted.